be in place for the semester. If it's going to change, I'll tell somebody else. But other than that, have fun and have a good semester.
Thank you very much, JR. JR is the one who keeps everything working smoothly. Thank you very much indeed. I will. Thank you and everyone to this first APS colloquium of the year. Oh, sorry about that. It's not even past yet.
They do start the recording 2 minutes early. Here.
Talk amongst each other for a while.
Perfect. Lovely. You can do an intro. How many? They get 1 minute. If you want to hand it off to me to describe like logistics. Well, no, whatever. I think just have them like. No, whatever. Perfect.
Welcome, everybody. Is this on? Yes, it's on. Welcome, everybody, to the first APS colloquium of the academic year. This is a round robin. There's a little timer up there, and in a little while, Zach is my co-colloquium team person, right? So just a few comments. I think we have 34 or 35 slides uploaded, and we have 1 minute each. That probably means that if you have a really important question that everybody wants to ask, go ahead and ask, and maybe at the end we'll have some collected questions for you to ask. Thank you to everyone who uploaded. Do you want to talk about the logistics of how this works?
Sure. All right. Well, hello. Welcome. Come on in, everyone. Plenty of chairs. So we have not changed the order of the slides in the Google Deck. So try to remember like who you were behind. But come on down. You can speak for up to 1 minute, and then hand the mic off and advance the slide to the next person, and then they can speak. All right.
We didn't change the order of the slides, but somebody did.
Take a look. If your slide appears, come on down and talk about yourselves. Lovely.
By the way, using up half of my half minute here, as you saw, there's some baked goods. And if you didn't already come to the APS office at 3 o'clock every week, next week it's Labor Day, so no colloquium next week, but there will be baked goods. And what we noticed is when Zach floated this idea and posted a sign-up sheet,
Ren
it got
suggested
filled in. Ren did this okay. It got filled in immediately. So it looks like the competition to make cookies is even stronger than the competition to upload slides to contribute in this thing. Should we go ahead?
Let's do it.
Let's go. And I guess I'm going to say a few words about this first slide. This was put together by Lindsay Nelson, our wonderful graduate office person up at the top there. And you can see here who our office staff are. Lindsay or Adele or any of the staff, would you like to make any comments? Apart from the fact that you have a wonderful staff.
Obviously, we have the best staff on campus. I'm not walking all the way down because I got in a fight with a curb. So as always, we have an amazing staff. I would actually argue our staff is much larger than this because we also are lucky enough to have the SBO and FIS staff included and here to help serve our wonderful APS community. If you have any questions at all, please don't hesitate to give us a call. We also are going to be putting out our calls for hourly student workers. That is both for helping out at our various different locations, whether it's SBO Fisk or at the office. You get to be one of the cool kids and hang out with us all day, which is super fun. So please keep an eye out for that in the Weekly Planet. Other than that, we're so happy to have you here.
Next slide, you're in charge of the pinger, right, Zach?
Great.
Our next slide is, again, put together by Lindsay Nelson, and it's a list of faces and names for our first-year students. I thought there were, oh, no. Come on. Leave it up.
I wonder, could we even put you, we know that you're welcome to our department. We know it's a little bit scary. There are a whole bunch of strangers in here. But if you're a first year grad student, could you just stand up and wave and say hello? We're so glad you're here.
You're part of our community, and I hope you will welcome the rest of us as your more aging counterparts or something like that. Okay, so the first years have a slide. We put on a slide for the second years as well. So, second years, would you like to stand up? Identify yourselves. Does anyone wish to make any statement? Okay. We do not have a slide for the third year students because you're on your own, along with the fourth and plus years. We have had some submissions from other graduate students, so you'll hear from some of our graduate students later on. Next slide.
1 minute, Andrew.
Dang! My name is Andrew Hamilton. I'm a full professor here. I've been here almost 40 years, and the focus of my current research is what really happens inside astronomically realistic black holes. And that requires one to understand high-energy physics. And so in the recent years, I've got more into grand unification and string theory and fundamental physics at its most fundamental level. I think there is a revolution to be made in this century. If you're interested in talking about physics, especially deep and fundamental physics, come to my office and we'll just enjoy life. Thank you very much.
Oh, you get two microphones. Well, do you want to keep introducing people? All right.
No, people are going to get this microphone.
Perfect. Thank you. Well, hello. Hi, I'm Zach Berta Thompson. I use he, him pronouns. I'm an exoplanet observational astronomer, so I'm focused on trying to understand the atmospheres of planets around other stars, mostly to try to figure out how they work in general, including here on Earth. I like using telescopes. I like rainbows. I like clouds. I like statistics. I like people. I like lots of stuff. So drop on by and say hi.
Rose, our planetarium, I'm our SBO person.
Hello, everyone. I do not run a planetarium. I do, in fact, run an observatory. I'm Rose Smith. I use she, her pronouns. I'm the manager of Summers Bosch Observatory. I've done a bunch of cool stuff, but right now I'm working on rebuilding our lovely solar telescope that's been broken for 2.5 years because someone left it on. I actually don't remember who, so I can't call you out. Yeah, there's some cool projects coming up, but I also want to introduce my two students. This is Anne and Melanie, and they are also going to say hello.
Hi, I'm Anne. I use she, her pronouns, and I work at the observatory. I'm a sophomore undergrad. Yeah.
Hi, my name Am I okay? Hi, my name is Melanie. I'm a second-year undergrad working at Summers Bosch Observatory. I'm a student in astrophysics. Later on, I am hoping to study exoplanets, solar physics, things among those.
Hi, it's really great to see so many people here. I'm Kevin France. I'm a professor in APS. I am giving a colloquium on November 17th, and I thought it would be really great to pre-record that and play it back at like 50 times the speed right now. And then in November, I would just take questions. I think that would be innovative classroom teach. Okay, so I have three things that I put down real quick, and I used half my time making jokes about what's happening in November. So like Zach, I'm interested in exoplanets and how they interact with their parent stars. I'm spending a lot of time now on the Rocky Worlds project. This is a 500-hour JWST and HST director's discretionary program to see if atmospheres can survive on planets around red dwarf stars. Probably not. So this is telling us that we're probably reaching the end of our capabilities with missions like Hubble and JWST, so we need to build new instruments to be able to answer new questions. So we do that with sounding rockets, like the Fluid rocket that'll launch in 2027, and the Mantis small satellite that David Wilson will also say something about quickly. That's the first light EUV telescope image there. You see that little blue circle? Yeah, so this will be the, thank you, first EUV telescope to launch since 1992, and this is all leading to our new great observatory, the Habitable Worlds Observatory. So I'm over time. Thanks.
Alex, are you here? He's not here. Oh. Hi. Alex can't make it because of East Campus shenanigans. Here's what he's up to in 2 bullet points. Making upgrades to the far ultraviolet integral field spectrometer in FUSE. It's a sounding rocket. And analyzing optical IFU data that he has of NGC 2366, a nearby dwarf starburst galaxy that may look like really old galaxies. And I presume that's him. Paul.
That's a tough act to follow. I'm Paul Hain, associate professor here in APS and at LASP. I'm a planetary scientist, and I'm interested in the way that planets in our own solar system and also smaller bodies like the moons of the outer solar system hold on to their atmospheres, and also how the ices on the surface record the history of climate on those bodies. So there are 3 examples shown here. I'm not going to name them. See if you can name which planetary bodies they are. One of them is the only moon in our solar system with a thick atmosphere. And one of them is a body that at its poles, like the moon, has deep, dark, permanent shadows that can hold ice for billions of years and hold a nice record of climate variations on it. So I'm also involved in instrumentation and space flight instruments, including some upcoming missions to the moon and other locations throughout the solar system, including the Emirates mission to the asteroid belt. So if you're interested in any of these things, I'm happy to chat anytime. Thanks.
Did David leave a message for us too? I gather David's not here either. But oh, no, this is totally my fault. He'll be here later. We'll come back to him. My bad. Thank you. Thank you for that. All right, Anna, you're up.
Hi, I'm Anna Zuckerman. I'm a 4th-year PhD student working with Sebastian Pineda in Dave Brain's group. And I work on simulations of auroral energy deposition in brown dwarfs. And that's sort of a schematic of how my simulation works. And on the other side is one of the interesting outputs you can get from that, which is basically where in the atmosphere is this auroral energy getting deposited, which has uses for understanding what we should expect to actually observe from these aurorae.
Right. Woo!
So hi, everybody. I'm Seth Hornstein. And I am a teaching faculty in the department, and so I have two hats. I teach classes, and I help direct Summers Bausch Observatory. Telescopes are much more interesting than classrooms. So I have a lot more pictures of telescopes, although I do a lot of teaching too. So I focus mostly, in teaching-wise, on the introductory non-major science classes, the places where it's going to be the last potentially science class that our students might teach or might take. So I'm really interested in that. I occasionally teach the upper-level observing and Python courses. But then also I have pictures of our telescopes. So for those of you who don't know, we have a 24-inch and two 20-inch telescopes. Those are the real ones. That is an amazing cake that one of our undergrad, Claire Lamont, made. If you know her at all, she's now a postdoc at Harvard CFA and has continued to make baking into astronomical things be part of her career. But I wanted to encourage anybody who wants to get involved at SBO. So we have open house nights on Fridays, which are almost all the way filled up. So thank you to the grad students for filling those up. Faculty, if you want to help host the open house nights, you are always welcome to. So please do get involved in the observatory if you want to play with fun telescopes.
G'day. John Keller. Fisk Planetarium is turning 50 years old. September 26, 1975 was the first ever program. September 26, 2025 is our kickoff celebration, followed by a year-long series of monthly events, musicals, Fran talking about the history of astronomy, astronauts coming in March. So check out Fisk 50th anniversary events. Also, we have a Science Under the Dome series. If you want to do Science Under the Dome talks, if you're a graduate student, come help us with that. We have a staff of 40, and Jeremy is going to represent all of them in a second, but they are an amazing group. My research is occultation research. If you're available on September 11th to September 12th UT, this is a shadow track that's going to pass over the United States. We have telescopes in all of these high schools and middle schools and community colleges, and the communities in Boulder, which is that little patch of things, is going to join them and measure that event. This is one of 6 events in the fall that will be measuring Trojan asteroids as part of a study of binarity of Trojan asteroids. Thanks so much, and we'll turn it over to Jeremy.
What's going to happen on the 26th of September?
Kickoff event, celebration, lots of wine.
Yes, hello everybody. My name is Jeremy. I go by he, him. I use he, him pronouns. I work on the Science Through Shadows project at Fisk Planetarium, which we've been working on for the last 2.5 years. We still have about a year left on that NASA grant. We make short films about the eclipses, occultations, and transiting exoplanets. So on the left, you'll see the 6 episodes that we have. We produce them in full dome and flat screen. So if you check out Fisk Planetarium YouTube, you can watch those online, or you can see them in a mini dome near you or a big dome over on campus. The 7 and 8 are the ones that we have coming up. And then the other part of my job is working on the music shows and concerts at Fisk Planetarium. So in the center, we have our 5 new in-house produced laser music shows. We used to have pre-programmed shows, but we have transitioned and we are making everything in-house now. So a couple different options for those new shows. The Flashback at Fisk that John mentioned, September 26th, will follow the Schmoozer event with a 1-hour laser show where we'll take basically 1 or 2 top songs from each decade from 75 all the way to 25. And there's a picture of the stuff we do.
I also have a cake on my slide. I'm David. I work down at LASP. I like looking at stars. These are some exoplanet host stars. If you have a star and you want to know what it's like, I will tell you what that bit's like. I will tell you what that bit's like. I will make up what that bit in the middle is like. I also like working on space telescopes like Mantis. This is a CubeSat we're launching in 2020 something, with the first EV astronomy telescope for decades. If you are an undergrad and have a major or minor in computer science and would like to work on Mantis, you have about 24 hours left to apply for a job with me. And I also like making cake. The end.
I see we have Dave here. Should we go back to Dave, or do we do... You're on next, Dave.
Okay, hi. I'm Steve Cranmer, professor here in APS for about 10 years now. I study the sun and other sun-like stars. I'm showing here is just, an illustration of how we use both observations and models to try to understand the physics of what's happening in like the outer atmospheres of stars, the hot solar corona, the expanding solar wind. That's sort of what we're illustrating. And my students and I do a lot of work sort of trying to bridge the gap between observations and theories. We're looking at data from the Punch mission that was just launched earlier this year, data from DKIST, the NSO's huge solar telescope, and still looking at some old 30-year-old data from the SOHO mission that's been languishing in archives and still needs to see the light of day. And and also later this semester, I'm giving another colloquium where you can hear a lot more about this. Thanks.
Zach, should we go back to Dave?
Sure, let's do it. David, come on up.
Okay, hi. My name is Dave Malaspina. I'm assistant professor here in APS. These are all the things I work on. So in the upper right is maybe the main thing, Parker Solar Probe. This is a spacecraft that has gotten closer to the sun than any human-made object and makes measurements in situ of the solar corona. And the idea there is to try to understand some of the physics that we can't by measuring things all the way out at 1 AU. We built a piece of that here at CU, the signal processor for the electric field and magnetic field instrument suite. We also build lots of other stuff related to electric field instruments. For example, the Canvas CubeSat electric field instrument, the Lucy lunar lander, which won't look exactly like that, but it's close. The cousin sounding rocket slated to launch in February, and actually the CubeSat launches in February as well. Van Allen probes, which studies the Earth's radiation belt, but has been decommissioned, and then MMS, which is still operating. So basically, I study wave-particle interactions in plasmas and how the energy transfers back and forth through those processes, and mostly try to do it with hardware and instrumentation. Thank you.
All right, John.
So I'm John Bally. I work on star formation, and what you're seeing here is a multi-epoch HST and James Webb campaign on a set of jets from low-mass stars, 300 kilometers per second flows. My general theme is feedback. How does star formation self-regulate itself? And I describe what I call the feedback ladder. Ever more powerful feedback mechanisms. And you have to realize that when stars form, the oldest, the most massive stars explode at the same time the lower mass stars are still assembling themselves. So feedback is a very complicated business. One of the things that we realized recently is that protostellar mergers are actually fairly common. The nearest massive protostar, Orion, underwent a merger about 550 years ago, produced a 10 to the 48 explosion. We still see it propagating through the cloud. We've now seen evidence for about half a dozen similar events over the last 10,000 years in the galaxy. That's it.
Hello, I'm Ren Cease. It is my second year in the department, and I was inspired by John to also make a GIF. So this is not stepping through time, this is actually stepping through wavelength. So we're going from broadband to like 1, 2, and 4 microns. So this is an extragalactic deep field survey that I'm helping run called Minerva. So a lot of what I work on is the connection between galaxy morphologies and then their physical properties, particularly their star formation histories. And it's just really fun to like watch all these itty bitty little star forming things light up as we step through these different medium bands. So those are strong emission features that you see just like boosting all of these specific regions in the galaxies. So yeah, that's mostly what I've been working on this year. Cool.
Hi, everyone. My name is Professor Anne-Marie Madigan. I have been here almost 10 years. Terrifying. This here is a real image taken from the Kuiper Belt. Oh, I forgot to say, I'm a dynamicist, so I work mainly on gravitational dynamics and different scales. What I'm really excited about right now is a project all about the Kuiper Cliff. And this is the image that I got when I plugged this into ChatGPT and said, could you tell me about the Kuiper cliff? So you'll see there's a Kuiper belt object and a cliff, and we're done. But this is basically the edge of our solar system, an edge in our solar system located in the Kuiper belt. And I'm trying to explain why it's there and why it's so sharp. Thank you.
Hello, everyone. I am Jane Bright. I was previously here as a visiting graduate student at the end of my PhD work. I then went away and was a visiting professor at Grinnell College, and now I am officially back as an NSF MPS SN postdoc fellow. Thank you. Working with Anne-Marie Madigan, who you just heard from. So I'm working on stellar orbital dynamics around merging supermassive black holes through computer simulations like this one on the left. I am also going to be working on developing a new PhET-style simulation for teaching the Hertzsprung-Russell diagram to students. Here is a very early prototype of that on the right. So if you teach with PhET or with lecture tutorials or are interested in active learning, I would love to chat with you and get your feedback as I develop this new tool for teaching. Thank you.
Okay, hello. My name is Ben Oppenheimer. I'm a CASA researcher, and sometimes I'm around here. Not much recently, but I'm going to be around here a lot more. What I'm showing here is a movie from a camel simulation showing the fascinating journey of cosmic gas, which I study, from the cosmic web through the circumgalactic medium and to the formation of galaxies at the nodes that you see there. I'm especially interested in galaxy groups because all galaxies pretty much live in groups. And this is just one of hundreds of, tens of thousands actually, of simulations that join cosmology, astrophysics, and hydrodynamic simulations with the aid of machine learning. And come talk to me maybe later this fall because I might have a Comps 2 project coming up. Thank you.
Adam, where are you?
I'm Adam Kowalski. I'm a professor in APS and at the National Solar Observatory, and I do solar and stellar flares. I was on sabbatical last semester, so you haven't seen me around, and this is one of the results, something that I worked on, which is first steps toward 3D radiative magneto-hydrodynamic flare model. So it's produced by the flash code. The photosphere is the bottom, corona on the top. And then a pressure pulse causes this explosion of material, shock waves going everywhere, maybe a Kelvin-Helmholtz instability on the right. This is something I'm currently working on. I'm really excited about. Another thing that I worked on was a new theory explaining how electron beams start at the top and get all the way to the bottom to cause that pressure pulse. That's an outstanding mystery. And don't tell the university, but I only just finished that on Friday, so.
Hi, everybody. I was too awkward to insert myself right after Anne-Marie and Jane. Maybe I should have done that, but yeah, I am now, I guess, a postdoc / instructor in the department. I just defended in May, and I work, thank you, I appreciate that. And I work very closely with Anne-Marie and Jane, but since Jane mentioned the supermassive black hole stuff, I figured I would talk about my other research project, which is actually related to white dwarf planetesimal debris disks. And so we actually, in our group, really love these weird disks we call eccentric disks, where all of these orbits are kind of aligned and all in this eccentric orbit. It turns out that white dwarfs, when they get this natal kick at the very, very end of the giant phase, the AGB phase, it gets this kick, and this kick can actually cause this eccentric disk. And when you get this eccentric disk, you can actually have planetesimals that can then become, very radial in their orbit and plunge onto the white dwarf, polluting the white dwarf. And this is something that we actually observe, are these polluted white dwarfs where we see heavy metals on the spectra of these white dwarfs. So that's the research project that I wanted to talk about. I'm super interested in this, so if you have any sort of feedback or things you want to talk about, let me know. And thank you.
Hi, my name is Teho. I'm kind of new. It has been 2 weeks. Ren said 2 years, but I 2 weeks. I'm destroying some stuff, especially stars. Well, of course, scientifically, I'm a very peaceful person. But I'm thinking about, destroying planets because I know many people are working on planets. But but I'm not your enemy. More scientifically, I'm interested in understanding the hydrodynamics and embody dynamics of observable events in galactic nuclei, globular clusters, and I became quite interested in mass transfer these days. And so these are some topics that I'm working on actively. And lastly, on a stressful day, if you want to break, let's break some things, Of course, astrophysically. Yeah, thank you.
Hello, I'm Yuta Notsu and I'm a RASP research scientist, mainly working with Adam and more people in RASP and SO. And I'm working on stellar flares and also interested in effects on exoplanets. I think flares don't destroy planets itself, but potentially destroy the atmosphere. And method, I'm working on multi-wavelength observations, ground-based tests, and X-ray UV. Especially, I'm mainly working with Apache Point Observatory. Actually, I had observation last night, so I observed until 6 a.m. this morning. Yeah. And in off time, I like going to mountains. Yeah. If you have any question about APO, maybe I may answer the questions potentially.
Hi, everyone. I'm Cole. I'm a sixth and final year grad student at APS. My sort of tenure at NSO and also APS has fortuitously coincided, I guess, with the advent of DKIST observations, which is the 4-meter class solar telescope in Maui. So I've had a couple of flare campaigns with the DKIST these last 3 years, and last August we collected the first observations of an X-class solar flare with the DKIST. This paper actually just came out recently, but we're measuring essentially the fine scales of the coronal loops in dark there, and then the structure and the bright ribbons. This image is in H alpha, and essentially I'm interested in how measuring the implications of studying solar flares in really high detail affects our modeling and understanding of how flares develop. So if you're interested in my work, come to speak with me or go see the paper at that QR code. There's also a press release coming out today. So thanks a lot.
Hi, everybody. I'm Emily Griffith. I'm a postdoc in CASA. Most of my research surrounds the origin of the elements on the periodic table, and I usually use high resolution spectra from large surveys like SDSS to study this. If you want to hear more about what I do, I'm giving an astronomy on tap talk tonight. Love to see you there. But I'm going to use the rest of my time to plug SDSS, which is an awesome survey that you should all be involved in. Boulder is part of SDSS 5, so you all have access to this data. There's a Milky Way Mapper survey, which is taking infrared spectra of millions of stars across the whole galaxy, as well as optical spectra of things like white dwarfs and M dwarfs in our solar neighborhood. There's the Local Volume Mapper survey, which is taking amazing resolution IFU data of gas and star-forming regions all around the galaxy. This is the Helix Nebula, and every pixel there has a spectra behind it. And there's also Black Hole Mapper, which is taking spectra of AGN, especially in time series to try and find changing look quasars. So here's an example changing look quasar, and they're also doing a lot of follow-up of E Rosita X-ray sources. If you want to get involved in SDSS, please come talk to me. I'm happy to tell you more.
Hi, I'm Whitney Powers. I'm a 6th-year grad student here at an APS.
I work on astrophysical fluid dynamics, looking at convection in planetary atmospheres and stellar interiors. This is a video from a project that I've been working on, one that I started with Ben Brown, looking at rotating moist convection. So this is convection with a phase change, and this gives us some quite interesting dynamics. So if this kind of stuff is interesting, find me and I'm happy to talk about it.
Hi, my name is Dolan Bhattacharya. I'm a research scientist at LASP. My research background is understanding upper atmospheric escape from solar system objects and exoplanets. On the left are 3 solar system objects that I'm currently working with, basically Mars, Uranus, and Earth. On the right are exoplanet projects that I'm working on. The top on top is the Cute CubeSat, which has been in orbit for the last 4 years and is likely going to survive for 1 more year. So we are going to get some more awesome ultra-hot Jupiter transits with this spacecraft. And then the last one is a newly awarded XRP project that I'm working on with Kevin Franz and David Wilson, where our goal is to understand the effect of enhanced EUV flux on the upper atmospheric escape of Earth-like planets. Thank you.
Hey everybody, I'm Nick Schneider. I'm faculty in APS. I've been here since the 2nd millennium. We'll just leave it at that. Often you've heard me talk about aurora on Mars as observed by the MAVEN spacecraft and our instrument made at last the imaging ultraviolet spectrograph. They're using a very high sensitivity mode of our instrument to look at the night side. But today, I'm going to talk about work by our early career scientists. And I see Sam and Caroline up in the back, and Jay may be here. And we actually have 4 more undergraduates on our team. So now you know our secret weapon. So they're using the lower sensitivity near ultraviolet channel that does imaging of reflected sunlight. And we get data that looks like this. It's very much like a visible imager, just the colors mean something different. So 10 years in orbit, and we're still learning new things. If you have a look, I'm going to increase the stretch on this. You all see that cloud appearing by the terminator there? That's a noctilucent cloud, just like we have on Earth, but they happen all over the place on Mars. And if you look closely, I'm going to stretch this some more, and you can see that that cloud extends farther and farther to the left. That cloud is not lit by the sun. That cloud is lit by the other cloud. And so this is an amazing phenomenon that goes nearly 30 degrees around from the terminator. You can actually see the little red line there, which is the at the edge of that cloud, that sharp edge of the cloud caused by the hard disk of the planet. Let me go at one more level here. If we turn on the high sensitivity auroral mode and say, how much sunlight did you see? That cloud goes 30 degrees around the planet. That cloud is 3,000 kilometers long. So while the first part that I showed you is very much like Earth noctilucent clouds, there is nothing like this elsewhere in the solar system. There's something special about the conditions on Mars that allow these clouds to pass the illumination all the way around that far onto the night side. So probably visible to the naked eye for when Matt Damon finally gets there. And in fact, this is going to be widespread on Mars, but we think it may be unique in the solar system. I invite you to think about why we don't see it on Earth or any other place. So we think this is going to give new insight into cloud formation, and we can even take a spectrum between the 2 clouds.
Hi, everybody. My name is James Crowley. I'm a 4th-year graduate student working at the National Solar Observatory with Kevin Reardon. I'm using DECIS data. DECIS is the Daniel K. Inouye Solar Telescope. It's a 4-meter telescope in Hawaii. I'm using high-resolution DECIS data to try to connect different layers of the solar atmosphere. Here I'm showing the magnetic field and the temperature retrieved from DECIS data at 3 different heights. Some other things I've been working on lately. I just finished writing an alignment code, which aligns data between different solar observatories. Right now it works with HMI and Hinode data, but I think it's adaptable to other slit scanning spectrographs. So if something like this sounds useful, reach out to me. I'm also starting a project where I'm using DKIS data designed to probe the structure of sunspot atmospheres using oscillations. This is with IRIS data, but we actually just got the DKIS data last Thursday, so I'm going to be starting that soon. So if any of this is interesting to you, reach out to me, and thanks so much.
Hello, everybody. I'm Ben Brown. I'm a professor in this department. I really like fluid dynamics, which a lot of you know from having to take fluid dynamics with me at various points. Some of you know it so much that someone greeted me today by showing me Kelvin Helmholtz instabilities that they'd seen over the summer. It made me so happy. I like studying fluid dynamics in stars and in planets, especially in planetary atmospheres. In stars, in our sun, I like studying how magnetism interacts with fluid dynamics, and we like looking at things related to the solar dynamo. So in particular, magnetorotational instabilities within the solar dynamo and just novel ways the solar dynamo may work. For planetary atmospheres, I've become really interested in rain. How does rain interact to drive motion in the atmosphere? How do the phase transitions related to it allow us to understand motion in an otherwise stable envelope? And this is a beautiful picture of a spring thundercloud up in Sunshine Canyon taken by John Keller. So I would love to talk with any of you at any time about fluid dynamics, math, or computers.
I can use my. Hello. I can do it myself. Okay. Hello, my name is Leon. I'm a third-year student in the APS department. I'm mostly interested in high-energy astrophysics, including plasma and radiative process around black holes. So I mostly use numerical simulation to study these actual very exotic systems. For example, I've studied the impact of low angular momentum accretion on the black hole, but due to limited space, I don't want to show it here. And recently, I have studied the impact of electron-positron pair productions around accreting black holes using 3D geometry simulations. And what I study is where do the pairs get into equilibrium in a black hole accretion flow, and the role of affections that brings pair into the upper corona and also outflows. I also study how the circularization of tidal disruption events of very deeply penetrating fully relativistic TDE. So what I find is that the circularization rate of these kind of TDEs seems to be quite low, which might challenge some of the state-of-the-art model of TDE that emission model that assume rapid disk formations. And I'm also interested in relativistic jet, especially striped relativistic jet, where you can have flipped sign of toroidal magnetic field along the jet propagation direction. And I'm trying to measure the magnetic reconnection rate along this jet. And yeah, mostly I'm just a simulation and black hole guy. So yeah, so if you have any questions, feel free to ask.
Hello, I'm Dave. I think I want to tell you three things if I can remember them. First, not only is this a pretty cool experience, but Earth is a pretty great place. I guess that was number one. We'll move on. The reason it's great is we have an atmosphere that allows for water to exist in a liquid state. It allows us to have this conversation by passing sound waves. It protects us from radiation. And I wonder how much you'd have to tweak the Earth-Sun situation and still have those things be possible. How far can you turn the various knobs of magnetic field, rotation rate, stellar type, amount of activity in the star? So that's one of the scientific questions that gets me out of bed in the morning currently, is what kind of planet orbiting what kind of star will hold on to an atmosphere long enough for that planet to be habitable? So that was one. Number two, we have kind of a large research group right now, about 14 people, thinking about questions like this, but the questions range all the way from cool plasma physics happening at Mars and Venus to what happened to the Martian atmosphere, to what kind of planet orbiting what kind of star, blah, 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 blah. And we have a lot of fun together. The third thing is that I'm also the department chair, and so I'm going to take prerogative. It's like, I only have one more year to do this, so. In addition to the thing at the Rayback, the Astronomy on Tap at 6 p.m., before that, from 5 to 6 p.m., there's a new majors welcome out on the Dwayne Quat. No, it's inside somewhere. It's now in D142. It's been advertised to the new majors, but feel free to stop by and welcome them before you either go to the Rayback at 6 o'clock or my daughter's back to school night at Fairview High School. Okay.
All right. I think that's it. Unless, does anybody have a slide that they think should be here but hasn't been displayed?
Does anyone want to introduce themselves who hasn't already done so?
Does anybody have any extraordinarily pressing questions from the amazing things they've heard about today?
I wanted to ask Anne-Marie about Planet 9. I'm absolutely, I'm so fascinated. And so what's the latest news? And
Not there.
Okay.
We'll talk more offline.
Sure. Can I amplify that question? Except I'm going to deflect it to Jane, because you had a lovely looking thing around a supermassive black hole. Could you actually explain what we were looking at?
Yeah. So yes, what you were looking at, we could even like go back to it, maybe. Up. Here's me. Play. There we go. Yeah. So what this is what we're actually seeing is each of those little dots is a star. The circles or ovals we are seeing is the shape of their orbits. The shape of their orbits is changing over time, right? So what this is this started as a perfectly circular disk of stars. Two black holes then merged in the center. The new black hole that formed from that then received a recoil kick. That recoil kick then reshaped the orbits of the stars around it into this nice aligned eccentric disk, like what Tatsuya was showing, that we also see in other systems. And then what this is showing is that the self-gravity of that disk, so the gravity of those stars on all of the other stars, actually serves to keep that alignment of all of those eccentric orbits over time, so they're not precessing out and becoming unaligned. The torques in between all of those orbits maintain this alignment, and then blue and orange is showing some stars are orbiting prograde, so in the same direction they were originally orbiting. Orange stars are orbiting retrograde, so opposite the direction they were originally orbiting, and that actually the interplay of those prograde and retrograde orbits are actually really important for maintaining that alignment through those torques over time. So there is a short version.
And yes or no, does that explain why there's no Planet 9? Yes or no?
Yeah. Yeah.
Now that I've had like a second to think, actually the project I'm working on the Cowper Cliff, the photo that I showed you from the Hubble Space Telescope, it's the interaction of bodies being scattered out in the outer solar system when they come in contact with giant planets. Those bodies actually torquing outer Kuiper belt orbits that can lead to a Kuiper cliff. There's a gravitational interaction that's really interesting. And then towards the end of these simulations that I've been running, the whole outer solar system collapses into one of these disks in a way that's getting a little silly, because everything I work on ends up being one of these structures in a very suspicious way. But that is actually the main driver of the Planet 9 hypothesis, that all of these orbits are distributed in this type of disk. So we do it without a Planet 9 again. So really, it's just not there.
All right, I think we should give everyone here a big round of applause and welcome.
We'll see you in 2 weeks.
Sounds great.
Meanwhile, talk to each other.